Swayam Prabha. Digital India. Educated India.
Or we could work out two more character tables. What do we want to do? Okay, let's do character tables today. I don't think time will permit. If time permits, we'll do the second one. Okay, so see the character tables that we have talked about already. C2V, C2V, C3V, so on and so forth. Even TD, they all have real characters, right? It is not necessary that character tables will always have real characters. Okay? Imaginary characters arise especially when we deal with cyclic groups. What are cyclic groups? Example? EC3 C3 square, which group is that? No. C3 group. C3, right? So what you are saying is that you only have C3, you have nothing else. Then the operations are C3, C3 square and C3 cube, which is E. Right or wrong? Or C4 or C5 or C6. Okay. What I am telling you is that the cyclic groups are groups which have these imaginary characters. So let us start with maybe C4. What are the characters? How many? Fine. All right. For a cyclic group, abelian group, we have said the cyclic group is abelian group. What does that mean? Everything is commutative. What else did we say about cyclic groups? Does a cyclic group have subgroups? Every element is a group by itself. Think of the C3 group. What are the operations? C3, C3 square, E. Now you cannot relate C3 and C3 square by any other symmetry element. Right? And you can work out the similarity transformations also. You will never be able to do the similarity transformation. So each is a class by itself. So how many rows should we have in C3? Say in C4, let us say. In C4, how many characters, how many rows should I have? 4. I'll call them gamma 1, gamma 2, gamma 3, gamma 4. We are trying to work out the character table. And what are the symmetry operations? E, C4, C4 square is also equal to C2 and C4 cube. What will be the dimensionality of each representation? 1. So I can write this first row and I can write the first column. Now we have to fill in the rest, but as we will see, not everything will be plus 1 and minus 1. If everything was plus 1 and minus 1, what would the character table look like? C2V. It is not. because you have a special relationship, they are not just independent. C4, C4 square, C4 cube. Okay, so let me do it like this. Let chi I of C4 be equal to x. So that would imply that chi I of C2 would be equal to how much? X square, and chi I of C4 cube is x cube. Okay. So I can write x square, x cube here. Now let me use great orthogonality theorem. This is gamma 1 is an irreducible representation. Gamma I is also an irreducible representation. So what can I write? 1 multiplied by 1 plus 1 multiplied by chi I C4 plus 1 multiplied by chi I C2 plus 1 multiplied by chi I C4 cube is equal to 1. Is equal to C4? 0. Okay. Let us do that. 1 plus x square plus x cube is equal to 0. How do I get it? I get it by gamma 1 multiplied by gamma I. Even this looks like gamma 1. Only pronunciation, nothing else. Gamma I. Alright? Very difficult algebraic equation, cannot solve. Can you help me solve? So I can factorize like this: x square multiplied by x plus 1 plus 1 multiplied by x plus 1 equal to 0. So x square plus 1 multiplied by x plus 1 equal to 0 implies that x is equal to minus 1 I minus I. Actually, it's a little confusing maybe, because here we have I and there we have I, but this I is not the same as that I, right? Not only am I different from you, this I is also different from the other I. What is this I? Iota. And what is iota? Square root of minus 1. So you can fill in these. So what will it be? 1, I have got what is x, right? So minus 1 I minus 1. What am I saying? Minus 1 I minus I. So I write minus 1, I write I, and I write minus I. What will this be now? C2 is C4 square. So what will chi C2 be? 1 or I, or minus 1 or minus I? Well, let us deal with 1 first. Let us write that 1. So what is C4 cube in that gamma 2? Minus 1. Achal, you with me? Understood? Sure? Okay. So then tell me what is this C2, chi C2? I square is minus 1. I is square root of minus 1. And what is chi C4 cube? Minus I. What is this C2, chi C2 here? Square of minus I. Square of minus I is minus 1 or plus 1? Sure? What is this? I or minus I? Sure? Or I cube? Even this is very nice symmetric, isn't it? 1i, 1 minus I and all that. Okay. Now, can we write the molecular nomenclature? First one is easy. I will write A. Do I need to write 1? Let us see. What is the second one? Gamma 2? Second one will be B, right? Because character of the principal axis is minus 1. So, antisymmetric. So, this is B. What about gamma 3 and gamma 4? What will I write? I cannot write anything. So, it is conventional to club them and name them E. So, say I do not need 1, 2 at all, A and B are enough. We club them and represent them as a 2-dimensional representation E. But do not forget that E is a reducible representation. In this case, if you add them, what do you get? 1 plus 1? I minus I? Minus 1 minus 1? Minus I plus I? So, this is written as E and it conforms, right? Because character of E here, character of identity is 2, which would make it a 2-dimensional representation, and we are getting it by adding 2-dimensional representation. Why do we like to add them up and combine them and write them together? Because that leads to elimination of the imaginary number. All right. See, in the reducible representation is 2 0 minus 2 0, no imaginary number at all, no complex quantity. It's nice. But do not forget that when we write E here, that is not the designation of the irreducible representations. Because we cannot write the designation, the molecular name of the irreducible representation so easily, we choose to combine two of them and write a combined nomenclature, a combined name. But E is actually reducible, right. So, if I give you 2 0 minus 2 0, you can easily reduce it to the constituent gamma 3 and gamma 4. All right. Question?
If I started solving this innocently, I would get the quantity for C2.
What?
If I start solving this innocently, just using the rate orthogonality theorem, I would get this as C2 even. Then how do I designate?
So, that is when you need to remember your group theory. What kind of a group is this? I mean, is that too complicated? So, what is the order of the group? 4. So, it is G4. So, if you remember, we had said that G4 can give you two kinds of multiplication tables, right? So, one kind of G4 is a cyclic group, the other kind of G4 is not a cyclic group. Okay? This is the first thing you have to remember. Secondly, you have to look at the symmetry operations. Looking at the symmetry operations, you can easily make out that this is a cyclic group, right? Right or wrong? There is nothing else, only C4 axis is there, nothing else is there. And with respect to the C4 axis, you can turn once to get a C4 operation, twice to get a C2 or C4 square operation, thrice to get a C4 cube operation, and 4 times to get identity operation. Okay, that is how you know. When it is a cyclic group, that is when your antenna should go up and you should think that now I should expect imaginary numbers. No, I just worked it out. Because what is the difference between this and that? You tell me. Between this and C2V. The difference is that there is no direct correlation. I mean, of course, everything is correlated, but then there is no direct correlation in the sense that I know that here the character of C2 has to be square of this. I know that the character of C4 cube has to be the cube of C4, right? There is no such relationship among the characters of G4 1, right? The symmetry operations are all different. Okay, so this is where you get the marriage of group theory and symmetry. One is not good enough. All right? Who has read ABCs of quantum mechanics? It's a book, I am not saying in a figurative sense. ABCs of quantum mechanics. So you are too young to, that book perhaps became extinct before you were born or something. It was by I think Steve Ridnick or Paul Ridnick, a small book, Russian, Mir Publications. So there the name of the chapter on bonding was Marriage of Atoms. So this is used very frequently in chemistry. Fine. So we have learned to work out C4. Now if I ask you to work out C4, you should be able to do it. If I ask you to work out C3, then also you should be able to do it. C3 is actually easier. C3. What do I have? I have C3 operation, I have C3 square operation, and I have E, which is equal to C3 cube operation. Once again, cyclic group. So how many representations do we expect? 3. Every operation is a class by itself. So 3, gamma 1, gamma 2, gamma 3. And L1 square plus L2 square plus L3 square equal to 3, which implies that L1 equal to L2 equal to L3 equal to 1. So these are all one dimensional representations. So I will write what I can write easily. I have only 2 places to fill. How do I fill those places? Let us say, now this is even easier, chi C3 is equal to x. What will chi, okay, I will write I also, chi I C3 square be? Very difficult algebra? X square. Very good. So what will chi I C3 cube be? Extremely difficult. Don't jump steps, tell me what it will be in terms of x, x cube, which is equal to your beloved 1. What is x? X equal to cube root of 1. How many roots should I get? What are they? 1, minus 1 and what? Oh, not minus 1? No, not minus 1, very good. So that will be equal to 1 omega, omega square. What is omega? Yes, that is right. And if I write in the exponential form? You are right, you are right. Anyway, I'll show it. I need the exponential form so that I can develop the other ones. So now see, I can write omega, omega square here. What will this be? And what is omega star? Omega square. So I can also write 1 omega, omega star. 1 omega star omega. And I don't exactly know why, but in character tables it's more than often it's written as epsilon. Epsilon is actually more general, but in this case definitely it is omega. Alright, so this is your character table. What is this? I can say this is A, and this together you call it E. Alright. Now what I will do is I will just show you some character tables of cyclic groups so that you get the general idea. See, C3 we have discussed already. And see, now you see what is the advantage of using E. When you use E, when you take xy and do this you make the symmetry operations operate on them, then they give you a reducible representation which is actually a sum of these two irreducible representations. Okay. So, you can say that x y jointly form a basis for this, r x r y jointly form a basis for this, and so on and so forth. Okay. So, this is C4 we have discussed already. Oh, okay, sorry, before that. So, this is the answer that Mehak did not know. Remember the form, e to the power 2 pi I by 3, e to the power 2 pi I by 3. Which group? C3. 3 and 3 rhyme, right? 3 rhymes with 3. Okay, C4 we have worked out already. Huh? What about C5? Here also you get something like epsilon, epsilon square, and so on and so forth. What is epsilon here? Epsilon is e to the power same 2 pi I but divided by 6. By 5, not 6. 5, 2 pi I by 5. And what is the point group? C5. So, again 5 and 5 rhyme. What about C6? Same thing, epsilon minus epsilon star minus 1 minus epsilon, etc., etc. Epsilon is exponential 2 pi I by 6. So, that is why it is convenient to write it in the epsilon form, because it will always become e to the power 2 pi I divided by p for this CP point group. Alright. So, this is how you can construct character tables which have imaginary quantities as well.
When we are clubbing two reducible representations together, how do we know which two to club?
In C3 it is very easy, you have only 2. Okay, let us see about C6 or C5. C5, see we have this is E1, right? 1 epsilon epsilon square star epsilon cube, and this is 1 epsilon star epsilon 2 star epsilon square epsilon. You get the message? Look at each column. Oh. वही कर रहा हूँ ना. Okay. Now can you see? And can you see? Huh? See? Epsilon epsilon star. Look at E1. Epsilon epsilon star in the same, under the same operation. Minus epsilon star minus epsilon, minus 1 minus 1, minus epsilon star, epsilon star epsilon. And here again you have minus epsilon star minus epsilon star, 1 1, minus epsilon star minus epsilon star. So, we have basically taken complex conjugates. That is how you club. Okay? It is all symmetric, symmetry rules. And that is how we get rules that govern symmetry. Okay. So, I think for once we have started on time and we are finishing on time. So, let us leave it here. If I start the next discussion, it will be too much. So, we come back on Thursday, and what I want to do is in the first maybe 15 minutes, I want to rush you through the normal modes of carbonate. I will share the slides with you already. Okay. And there, the reason why I want to do is more than anything else to show how you can decompose a complicated reducible representation into its constituent irreducible representations. We will do it all the time for the rest of the semester. And then we would like to go on and discuss a little bit more about the relationship of symmetry with quantum mechanics. What is the role that symmetry plays in quantum mechanics? In fact, that is what the rest of the course is about. Once again, we are going to see how you can use symmetry to factorize things like secular determinants. right? But before that, we will perform on Thursday a general discussion of the interplay between symmetry and quantum mechanics. Then we learn something called symmetry adapted linear combination, which is of utmost importance for us to develop things like molecular orbitals. Okay. Once we are done with that, while doing that, we will also learn something about a very useful tool which is called projection operator. Okay. Once we are done with that, our arsenal is complete. We know all the tools that we need to tackle actual chemical systems. So hopefully this will get done, if not on Thursday, definitely on Monday. Thursday and Monday, these two classes, we will be ready with all our tools, and then we attack chemical problems full-fledged from next Tuesday onwards.